Welcome to the next session of Demystifying Blockchain, where we will speak about blockchain in enterprise.
Thank you, Julia. So today we will be discussing the different types and evolution of enterprise architectures for enterprise applications. Specifically, we will be diving into the evolution from monolithic applications and their development and operations, going to service-oriented architectures, and then the current wave of microservice architectures. And we'll finally conclude on how microservice architectures, when combined with blockchain technology, we arrive at the Leia architecture, the Luther Enterprise Infrastructure Architecture, which provides many of the benefits of microservice architectures without some of the drawbacks that those new types of architectures can introduce. So going back to the beginning, so enterprise applications, this is software that is deployed within large organizations. So think things along the lines of enterprise resource planning, ERP systems, customer relationship management systems, supply chain management, business intelligence. There are many different applications that exist within a large company that enable business processes and enable employees to conduct their day-to-day business. These are typically really large applications that are very configurable and customizable, and they can be designed typically as an end user. You wouldn't really see the kind of what happens behind the scenes, how these applications are developed and the different architectural choices. You would just interact with these applications, in today's world through a web interface, but in the past through desktop applications, or it might be just through interacting with people that behind the scenes are using these software as desktop applications or web applications. And but normally, from an end user standpoint, as someone within the enterprise, you wouldn't really have too much insight as to how these applications are designed. You would probably hear of large companies like Salesforce that are offering these kind of services, but you may not have insight as to how they're built. And so we will dig into and kind of lift the veil and see what happens behind the scenes here for how these applications are designed and the different trade-offs. So traditionally, these large enterprise applications, they're very difficult. They're very customized. They have to serve a lot of different business needs and custom business requirements. They're difficult to build in the sense that these companies like Salesforce have invested a lot of engineering into making sure that these systems are robust and reliable, at the same time flexible to all the different use cases and all the different customers, each with their own, at times, custom business logic. And throughout the years of building these applications, there's a landscape of different products and horror stories as well as success stories. And throughout the years, there are certain designs, the way you build this software, there are certain approaches which have proved more successful and more effective than other approaches. So in the traditional enterprise application, so think like enterprise resource planning software or a claim processing system. There would be a presentation layer. So this is a user interface that an end user interacts with. In the modern world, it's a web application. This is what the user is pointing and clicking and typing into. There would be a back-end system. This is a server that is receiving messages that are requests that are being generated from that UI, and there is a database which that backend server interacts with. And the combination of those three things as a whole it constitutes the traditional monolithic architecture. And what that means is mainly focusing on the backend piece, it's one large unit. So it's one unit of development, one unit of operations, and typically one unit of deployment. So from a practical standpoint, that means you have software developers that are making changes to that single piece of software. It's a computer program. It's a process that's running on a server. It's a very large process. In some cases, you think along the lines of millions of lines of code for these legacy enterprise applications. These are massive. And so you have typically a single team in the monolithic architecture. You have a single team of developers that are writing code and doing updates. These developers are using typically object-oriented design, so they might break off this large application into different sections of code or different files or classes, if you're familiar with object-oriented programming, to isolate different parts of the code and provide structure. But at the end of the day, in the monolithic architecture, the back end is one large process that's running on a server. And so in the very beginning of enterprise software, that this is how this is sort of the first architecture. And the advantages of the monolithic design is, the biggest one is simplicity. So your deployment strategy, it's a very simple story. You have this one piece of software running on this single server. You have your development team. They make some updates, and then when it comes time to rolling out a new version, they are either restarting the server or they are stopping and starting a new version in a graceful way, so that you don't lose, so that the server can still serve requests while it's being updated. But you're updating the entire process as a whole, as a single unit. So the operations side. So the development side, you have one team of developers that are familiar with the code base. Maybe they have separate files that the team might be split up where people are working in different files or different libraries or modules, but using object-oriented programming. But ultimately, you get this one computer, this one process, this one piece of software. And on the operations side, you have an operations team, which would be separate from the development team, and the operations team would be responsible for for making sure that that one process is behaving correctly. They're monitoring it, making sure it's up, it's servicing requests, looking at the resource usage, and making sure that its resource profile is adequate for the server it's on. All of these things. And then that operations team, when there's an updates to that software, they get a new version. They would then bring down the old one, bring up the new one as a whole unit. And that approach, so pretty simple story to explain from an operations standpoint and from a development standpoint. The problem with the monolithic architectures is that that single server, that single process, ends up having difficulty scaling. And scaling meaning a few different ways. So in the most literal way of being able to process more requests and have higher performance, it can have issues with that since it's a single process. It's not straightforward to, typically the scaling story is you just buy bigger machines. You just run it on more expensive hardware. But you sort of end up reaching a limit with that depending on the size of the application, and that will only go so far. Also scaling from the perspective of the teams involved. So in the monolithic architecture, you have a single development team working on this large piece of code. So you have to keep your development team relatively small before things get massively complex. So having more than just a handful of team members all working on the same piece of software becomes very difficult to coordinate. You end up with what I've seen in the past is you end up with things like individuals carving out different sections of the code, a lot of repetition, a lot of the same services or libraries are being kind of re-implemented in different sections of the code because it becomes so large that no individual person has insight into the entire system. And so the complexity of the code increases. It's difficult to have larger teams work on that single code base, do the communication and the coordination effort that's required. So it's difficult to scale the development team. And then on the operations side, similarly, there's only one sort of one process that they operationally is being managed, and so from an operations standpoint, it's quite a simple story. But again, the application quickly becomes overly complex. It tends to be slow. It can't meet the performance requirements. There are also scaling from the perspective of resilience and reliability. So oftentimes monolithic applications introduce a single point of failure because there's only one backend server that's running. It might be a very large one. So if that goes down, another one has to be turned on, and sometimes you can do things like failover and have redundancy, but it's not part of the core architecture or the core design typically, and so you end up with a single point of failure, and you can't scale out to continue servicing a large number of requests when failures occur. So due to those types of limitations, folks started looking at new architectures that go beyond monolithic to overcome some of those limitations. And the next architecture in that evolution is service-oriented architectures, or SOA. So I would say the apex of this, and it's still, there are still a lot of, and just to be clear, there's still a lot of monolithic applications that are being developed today, especially if you're doing a new project or a proof of concept. It can be quick to get off the ground with a monolithic architecture. However, with these limitations in mind, folks started to look at alternatives, and we ended up with service-oriented architectures. And the height and I would say apex of SOA was in the early 2000s. So a lot of the large legacy Java applications that are deployed in production today that we see, a lot of them are SOA architectures. And so the idea in SOA there was, instead of having this one back-end process that's servicing all the requests, the architecture splits that back-end process into several processes that are then communicating with each other using message passing based systems. So think either there's an appliance called an enterprise service bus. But you can think of that as a central message queue that delivers messages between these different services. So you can break up your monolithic application into a handful, think on the order of like 4 to a dozen. So not a huge number, but a handful of separate services that are isolated in terms of their functionality. So think you may have in the SOA architecture, you may have a service that's responsible for authentication, and that's all it does. And Other services would, when they receive requests, would use that authentication to be a consumer of that authentication service in order to authenticate and authorize requests that they are processing. So you end up with these handful of services that are communicating using typically an enterprise service bus, which is just a message queue that is routing the messages between these different services. And each of these services are transforming these messages and making requests. Other types of the enterprise service bus, this queue typically isn't in the traditional SOA architectures. It's not just a message queue. It also provides things like logging, error handling. It might do some message transformation. In terms of some of the technologies that and standards that were being used at this time and in these architectures, SOAP XML is a big one that you see all over the place. So you end up with these handful of services all communicating over a message bus, where that message bus is a pretty large process that is providing additional services like the logging and the message transformation, error handling. And in some cases, the service bus itself is authenticating requests and enforcing policies like defining which services can talk to each other, and routing the requests across these services. And that's that new architecture, the SOA architecture, is great because now you can have more than just one team being responsible for the different components of your architecture. So I mentioned the authentication service earlier. So now you might have a invoice processing service. You might have an authentication service, and you can have the invoice processing service be developed by a separate group of people than the authentication process. So now you can have two teams that are developing the software independently and being able to specialize in exactly what that service does. And so instead of having, like in the monolithic architecture, instead of having these large complex applications where nobody really understands the entire application, now you've broken it up into smaller parts where each team can fully understand their individual specialized part, and then you have communication using these enterprise service buses. So the main benefit of that is by going beyond. It allows the application to be developed in a more modular and isolated way by separate teams. Now, I mean, that's the dream. In practice, a lot of SOA architectures are actually very tightly coupled, meaning the individual services. So I mentioned this authentication service and this invoice processing service. Although they are separate services within your enterprise application, they can't be reused across separate projects. So usually they're specific to that single application. So yes, you can have separate teams developing them, but it's not as modular as you would like. You can't just pick up one of these authentication services, let's say, and just drop it into another project or reuse it across multiple projects. That typically in the design, specifically around these message patterns, the way the services communicate with each other, they're very tightly coupled. So they have very specific message formats. The enterprise service bus has a bunch of business logic in it that's specific to that application, and so it reduces the reusability of these services into other services, into other applications. And so in practice, although the different services can be developed by separate teams, because the message patterns and communication patterns are more of a request response or imperative or command type patterns, you end up with only a handful of teams in the best case. So think on the order of like 2 or 3 teams working on these separate services in a large SOA application. Additionally, a limitation is that your enterprise service bus ends up being very complex and oftentimes a single introduces scalability problem. So it's difficult to scale this enterprise service bus because it's doing a lot. So it's more than just a message queue. It's actually performing these other functions that I mentioned, like the logging, the error handling, message transformation. It's doing a lot, and it ends up being difficult to scale in order to meet the performance requirements of these services passing messages to each other. So because of this, SOA architectures oftentimes end up you have the tight coupling. You end up with they end up being very more difficult to operate in production. So you end up, like in the monolithic architecture, although they're separate services, they end up all being managed and operated as a single unit, and you don't get the scaling benefits that you would like from the operations side, where you can have multiple operations teams, let's say, be responsible for the different services. In taking a step back in terms of operations lifecycle, so typically both in monolithic and SOA architectures, the way these applications are managed operationally is you would have a separate systems operation group. It's a separate group that is responsible for tracking the health of the application, the monitoring and reporting. There might be a network operations center that's responsible for monitoring the network and the messages that the applications are sending on the network. It could be triggering alarms when there are issues on the network, like messages being dropped or applications not responding to like health checks, or if an appliance crashes, or an application crashes. Maybe this enterprise service bus, you might have performance metrics like the number of messages per second that are being processed. If that exceeds or drops below different thresholds, the NOC, the Network Operations Center, may trigger alarms. The operations is sort of separate from the development. They're two different teams. They're not the same people in monolithic and service-oriented architectures. So oftentimes there's not a feedback loop between the developers who write the applications and how the applications operationally behave. They're two entirely different groups. In many cases, I've seen that the teams aren't even in the same location. Typically, in many cases, the operations team may be in another country, and the development team would sort of throw updates to the software over the fence, so to speak, and then the operations team would then be responsible for making it be deployed in production and monitoring it and applying those updates. And in the monolithic case, it's one large file, like a jar file, that's being thrown over the fence, or a WAR file in these Java applications. And in the SOA application, it might be several for each of the different services, and then the operations team is responsible for deploying that and updating the specific service. So because of the limitations of these SOA architectures, recently, like as in the past, I would say 5 or 6 years, there's been a huge amount of interest in what are called microservice architectures. And this was mainly popularized by Netflix initially. They had huge scaling requirements, a huge amount of interest as they went to provide streaming services, and SOA wasn't meeting the scale that they required. And scale meaning both having the system be able to process a certain number of requests per second, as well as being able to have larger development teams that are building out all the different features that Netflix requires. And so the other thing I should mention too is in these service-oriented architectures and monolithic, in monolithic architectures, they're all written typically in the same programming language, and usually in most cases it's Java. Which also limits like how scalable your team is, because now you're only tapping into a talent pool that knows and is interested in writing Java applications. And so to address these concerns, Netflix really popularized publicly microservice architectures. And the idea there is now you're splitting up your application into even smaller components. And you're having separate teams be responsible for these individual components, both from a development standpoint as well as from an operations standpoint. And these smaller components are known as microservices. They intercommunicate typically either directly using REST JSON APIs, or there may be a message queue that is a lightweight message queue. So think of technologies like RabbitMQ or Redis, that type of thing, not these large enterprise service buses. So scalable message queues that don't do much, they do one thing very well, passing messages between services, publishers and subscribers. And because the communication is either direct using REST JSON or it's a scalable message queue, these MSA architectures can meet the performance requirements necessary for services like Netflix, which at one point had a huge percentage of the overall internet traffic on the internet just for streaming their services. So the microservice kind of philosophy is for these individual services is do one thing and do it well. This is a carryover from the Unix philosophy of how the Unix systems broke their tools into small individual tools that do one thing and only one thing well. So it's not this goes against sort of a Swiss Army knife approach where you have tools that kind of do 10 different things, but probably not any single thing very well. So now you have, instead of that, you have 10 tools, and they each do that very well. And then the other Unix philosophy that they've also adopted is the concept of smart endpoints and dumb pipes. And what that means is you don't put a lot of complexity in your message passing system. So you don't have these huge enterprise service buses that are transforming messages and doing logging and error handling and all that. Instead, the network or the piece of software that's passing the messages and routing the messages between these different services is very minimal in the functionality that it provides to the services. It does one thing and does it well, and what it does is pretty dumb. It just takes a message, routes it to the destination, and does that reliably, and that's pretty much all it does. And because of that, the network can scale and no longer becomes a bottleneck like in a SOA where you have an enterprise service bus. The microservices themselves are loosely coupled because instead of having sort of the traditional command or request response messages that are specific to individual services, which creates a type coupling between the services. Now you're looking at APIs. So you're looking at an agreed upon standard that is useful, that isn't specific to another application using that API. So so your service, it provides in terms of like, let's say the identity management software, it would provide an interface to other services that looks at that like validates requests, and that's all it does. And the way it does it, the interface from an external service standpoint is very simple and not specific to the consumer of the service. So it does authentication or identity management services, and that's all it does. And this is the API, and the API is not specific to the consumer. And so what that means is by having an API-driven approach, is you have this loose coupling between the services, and the microservice doesn't have to be aware of the consumers of the service and how they're processing the data or why. It's just offering a service that meets this agreed upon API. And this loose coupling is ultimately what lets you have separate teams develop and maintain these separate services. And in Netflix's case, I believe they also enabled polyglot systems, so meaning just multiple programming languages. So instead of in the SOA and the monolithic-based designs where you had everything written in Java or C# and .NET, you have different microservices written by different teams. Some of them are written in Java, others are written in Node.js. Now you're seeing a lot of services written in Go, and so you now can scale your development team, because now you're not just looking for one type of developer that wants to write Java. Now you're looking at a much wider pool of developers that can work on the project and have their and be able to build out functionality in the end, like in the Netflix case, in the end product, without having all these communication overhead or strict requirements as to the type of language or libraries or communication patterns for these different services. And so this also around the same time. Well, I should mention. So we've mainly been focusing on the back end service part, but I should mention too that in the database, from a database standpoint, in the SOA architectures, and of course in the monolithic architecture, there would be one database. So you would have a database service that provides data persistence to the other services in the SOA architecture, and in the monolithic architecture, it's just a single database that your program would read and write to persist data. And in the microservice architecture, because each of these components are loosely coupled and they're just exposing their interfaces through APIs, these agreed upon standard ways that aren't specific to the consumers of the APIs, you end up with each microservice being able to have its own data store. So it frees up the underlying persistence layer. So instead of, like in the SOA architecture, everything having to be written on top of an Oracle database, let's say, in the microservice architectures, what you're seeing is the different services are able to have not just their own programming languages that might be more applicable to the problem that the microservice is solving, but also their own database technologies. So you might have some microservices that use key value stores if that's the most efficient or makes the most sense for the services that microservice is providing. Then you have other microservices that are using SQL, like relational SQL databases, if that makes more sense for the kind of operations and APIs that the microservice is providing. And so ultimately you're improving scalability as well as decentralization over SOA. Decentralization meaning you're moving beyond just a single team maintaining your application. You now have you actually have separate teams each developing their own microservices and maintaining it. Because the microservices are just exposing APIs, you now can build, you can have multiple applications use those same microservices. So instead of in the SOA approach where the service is isolated to that one enterprise application, in microservice-based approach, you deploy your microservice, and then anyone in the company, depending on the permissions or any other applications in the company, can now be a consumer of that microservice. So you end up having multiple applications using the same microservice. So you end up with code, you end up with reusability and being able to reuse services beyond just one particular application. Now, I should mention that microservices has also coincided with the development of this concept called development operations, DevOps. And now, so in the monolithic and SOA architectures, we mentioned how you have a development team and an operations team. The development team throws a jar or a WAR file, throws a new version of the software over the fence to the operations team, and the operations team, which is in many cases in another country, will then go off and make sure everything's running in production. And I mentioned how there's a disconnect there. There's not a good feedback loop because they're two separate functions. Sometimes they're in two separate departments of the company, and microservices goes hand in hand with DevOps, and the idea there is that the developers not only are they responsible for developing their microservice, but they're also responsible for the operations of their microservice. So the operations deploying a single service, typically this is using containerization technology. So instead of deploying a single monolithic service, now developers are using containerization technology and doing a DevOps mentality where the developers are operating and monitoring their microservice in addition to developing it. And this lets you have a tight feedback loop, and developers can be closer to how their applications are behaving in production, which ultimately results in better, more reliable applications microservices being developed. Now, okay, so we talked about monolithic, SOA, and microservices. And in terms of the time frame, think monolithic, like, from the very beginning of mainframes up to, well, they're still used today, but really up to like early 2000s. SOA being early 2000 up until maybe 2010, 2012, in that kind of range, and the microservices kind of hitting the scenes over the past 5 or 6 years. And now, we talked about the benefits of microservices. The problems are that you end up with a bunch of the different microservices with a bunch of different technologies and a bunch of different databases and data stores. And so as an ensemble, the system can end up being a lot more complex. And you end up with data stores that these microservices, it becomes operationally, although each individual group is deploying their microservice, and you're doing a DevOps model, you end up with many of these microservices communicating in their own custom communication patterns, point-to-point or message bus, their own programming languages and database technology. And so you end up, in many cases, with a much more complex operational system where you have less visibility in terms of which processes are communicating with other processes, and you end up with a reconciliation problem where these microservices become out of sync and don't see the same type of data, and And so although from a single microservice standpoint, operationally things look simpler, from a holistic standpoint of your entire system, things become a lot more complex. And particularly when things go wrong, it can be a lot more difficult to troubleshoot and identify where the problem was introduced and what exactly went wrong, because now you have all these different technologies, these different databases, these different message passing patterns, queuing systems. And that brings us to Leia, the Luther Enterprise Infrastructure Architecture, which is a microservice-based architecture, but we're introducing blockchain technology in order to address these concerns regarding visibility, these data silos, data reconciliation, and as well as security for these different services. And so so you can think of Leia as a blockchain technology plus microservice-based architecture. And ultimately, the Leia architecture overcomes these types of problems that microservice architecture introduces, while keeping the benefits, these decentralization and scalability benefits that we mentioned that microservice architectures provide. And the way it does that is by using blockchain technology as the communication layer between the service orchestration layer between these different services. So instead now of the different services, instead of the different services communicating in a point-to-point way with their own data silos, now they can coordinate and communicate through smart contracts executed on underlying blockchain technology to reliably and transparently and securely execute these business processes. So you can think while maintaining decentralization. So you can still have the separate teams have ownership of their individual services, but now these services are being coordinated through smart contracts that are being executed amongst the different participants. And I would like to pause here, and then during the next session we will dive into the exact details of Leia and how that works.
Great, thanks, Sam. So actually, while going through the session, you answered half of my questions. So I would just have two more. So I know you said all of the, like they kind of appeared throughout time, but you said even monolithic, which was used as the very first one, it's still used today. So I was wondering, is there any possibility to say approximately how much percentage each of those are used, or at least which one is kind of used the most today?
Yeah, no, it's a good question. I think well, so there are many applications that are legacy that were developed in like the early 2000s or earlier that are still operating and chugging along today in the enterprise. I mean, you still hear about these large mainframe systems that are ancient and that are still chugging along, and so mainly because of the legacy systems, I would say there are a large percentage of enterprise applications that are monolithic. If I had to guess, I would say probably around 50 to 60% at least are monolithic. Of the enterprise applications that are in production today are monolithic, and I would say and most of those are probably legacy from an earlier time. Beyond I would say the remaining like 30 or 40% are SOA architectures, and then it's just recently microservice architectures have hit the scene over the past few years, and I would say most of the applications that are being developed today are microservice-based design, and that the industry is quickly moving to that. But many of the applications are that are in production are legacy and carry over from an earlier time.
Okay, yeah, understand. And the second question I was having, so with microservices, you mentioned particularly Netflix. So I was just wondering whether Netflix actually invented microservices or if they were kind of the first ones who used it and kind of made it popular.
They were the first to widely kind of publish their successes with microservices. A lot of these large Silicon Valley tech companies are notoriously secret about how they build and design their applications. But I mean, some things have come out over the years. I would say Netflix is the most vocal and was the first to really very outspokenly praise the benefits of microservice architectures. But since then, we've learned that like Google, for example, many of their services are they've adopted microservice architecture for a long time, and then probably the Facebook, Uber is probably the most famous in terms of like recently their adoption of microservices, where you're looking on the order of like hundreds of thousands of microservices. Like it's almost like nano services. Like they've taken it to like a whole nother extreme. But in terms of who first invented it, I think it's difficult to tell. But I don't think it's Netflix. I think people have been using similar architectures. It's just Netflix was the first to be quite outspoken and vocal and really be a proponent of this type of design.
Okay, great. Thanks. So that's it on the first session of Blockchain Enterprise. And the next time we will revisit and talk in more detail about the layer architecture.